Have you ever paused to think about how much we learn every single day, almost without realizing it?
Hmm.
From those first wobbly steps as children to remembering a quicker route to work after a few attempts, our brains are constantly making decisions, adjusting our behavior, and refining our strategies based on the outcomes. It's an incredible adaptive process that happens within us all the time.
It really is. Yeah.
But what if we could bottle that ability? What if we could give that kind of autonomous, self-improving intelligence to a machine, allowing it to solve problems too complex for us to explicitly program,
Ah,
problems that evolve and change, requiring a system to figure things out for itself through pure experience?
that's a profound question, and it really does sit at the very heart of modern artificial intelligence.
Right.
The idea of a system learning from its own direct interactions, forming its own understanding of what works, rather than simply following predefined rules, is what unlocks so much of the potential we're seeing in AI today.
Exactly. And that's precisely the journey we're embarking on today. We're delving into the foundational algorithms that power this kind of adaptive intelligence.
Hmm.
We're going to unravel the powerful ideas behind dynamic programming, then explore Monte Carlo methods, and finally, look at the elegant fusion of these two, known as temporal difference learning, particularly its advanced form, TD.
Sounds like a great plan.
You've provided us with some truly excellent source material, and our mission in this deep dive is to not just define these concepts, but to make them crystal clear, giving you those aha moments of understanding through concrete, relatable examples.
Yeah, make it intuitive.
We want you to grasp not just what these methods are, but why they are essential, how they actually function at a core level, and where each one truly shines in the grand landscape of intelligent systems.
Our goal is for you to walk away with a solid, intuitive understanding of these core algorithms. Think of it as a shortcut to being well-informed, equipped with the knowledge to appreciate the subtle genius behind machines that learn to make smart decisions.
So, let's begin by setting the stage for this exciting exploration. Before we can appreciate the solutions, we first need to understand the problem these powerful algorithms are designed to solve.
Makes sense.
And that problem is known as reinforcement learning, or RL for short. Expert, in the simplest terms, how would you define reinforcement learning?
Reinforcement learning isn't just one thing. Think of it as a grand challenge for AI, a
Mm.
set of brilliant tools to solve that challenge, and a whole academic discipline dedicated to figuring it all out.
Okay.
At its heart, it's about an agent, that's our learner and decision maker, interacting within an environment.
Right.
The agent's ultimate objective is to learn what to do, how to map the situations it encounters to specific actions, all with the explicit goal of maximizing a numerical reward signal it receives over time.
A reward signal. Okay.
It's a closed-loop system where the agent's actions directly influence its future inputs.
That sounds remarkably like how a child learns, or even how we train a pet. They try something, they get a positive or negative reaction, and they adjust their future behavior.
That analogy is spot on.
So, what are the truly defining characteristics that set an RL problem apart from other types of machine learning?
That analogy is spot on, and it highlights the three critical distinguishing features of RL. First, and this is fundamental, it's a closed-loop interaction.
Close loop.
The agent's actions aren't just one-off events. They directly influence the inputs it receives moments later, changing the environment around it. Imagine a robot exploring a house to clean it. Its decision to enter a new room fundamentally alters its environment, potentially revealing more messes to clean, or perhaps encountering a low battery warning.
So, every action creates a new scenario.
Precisely. The second characteristic is that there are no direct instructions.
Ah, okay.
The agent isn't explicitly told which action is correct or incorrect.
Right.
Unlike supervised learning, where you have labeled examples telling the system exactly what to do, an RL agent must discover the best actions through trial and error. It has to experiment, observe the consequences, and figure things out for itself.
Right, like trying to teach someone to ride a bicycle. You don't give them a perfect instruction manual. They have to get on, try, wobble, fall, adjust, and eventually, through that direct experience, they learn.
Absolutely.
Yeah.
And that brings us to the third crucial point, which is often the trickiest to grasp: delayed consequences.
Delayed consequences.
An action might not just yield an immediate reward or punishment. Its full impact, whether beneficial or detrimental, could play out over an extended period, many steps into the future.
Hmm.
The best action right now might only offer a small, immediate reward, but it could open up a path to much larger long-term rewards down the line.
Okay, that makes a lot of sense conceptually. Can you paint an even clearer picture of this interaction, this continuous loop between the agent and its environment?
Certainly, visualize a never-ending cycle. At each discrete slice of time, let's call it tet, the agent receives a representation of the environment's current state, which we denote as saint.
Got
Ba-
the
Based on this state,
right.
what it perceives and understands about its situation, the agent then selects an action, at.
At.
One tiny moment later, the environment responds to that action. It provides the agent with a numerical reward, archt plus 1, a scalar signal, like +1 for success or -1 for failure.
The reward.
And it transitions to a new state, same +1. This loop continues. The agent is strictly the decision maker, the learner.
Right.
The environment is everything else that the agent interacts with, everything outside its control. This boundary is critical.
Right.
It defines the limits of what the agent can directly manipulate, not necessarily the limit of its knowledge.
Interesting distinction.
For instance, our Rubik's Cube solving agent might know all the mechanics of the cube, the environment's rules, but it still needs to learn the sequence of actions to solve it.
So the agent's ultimate objective is to maximize this reward signal, but you emphasized cumulative reward over the long run. What's the fundamental insight there? Is it about patience, about long-term vision in AI? How do we even formally measure this total cumulative reward in a way that makes sense for a machine?
That's a crucial distinction. It's not just about a temporary win, but the ultimate prize.
Right.
The fundamental insight is captured by the reward hypothesis. All goals and purposes, no matter how complex, can be thought of as maximizing the expected value of the cumulative sum of a received scalar signal, reward.
Okay, the expected value, cumulative sum.
The agent's sole objective is to maximize the total reward it receives over the long haul, not just chasing immediate gratification. Consider that chess-playing AI again. You wouldn't reward it for taking an opponent's piece, because that might be a tactical blunder.
Ah, good point.
You'd only give it a reward for winning the game. Otherwise, it might learn to capture pieces, even if it means losing the overall match, which defeats the true objective. It's about aligning the immediate feedback with the true long-term goal.
That makes perfect sense. It's about defining the true objective, the overall success. So how do we formally measure this total cumulative reward for the agent?
We use a concept called returns, denoted charade. The way we calculate it depends on the nature of the task. For tasks that have a natural ending, like a game of tic-tac-toe or navigating a maze to a specific exit, we call these episodic tasks.
Episodic, like an episode of a show.
Exactly. Here, the return is straightforward. It's simply the sum of all rewards received from time 2 until a designated final time step t. So gt equals rt plus 1 plus rt plus 2 plus rt.
Like getting a final score at the end of a video game level.
Exactly. But many real-world scenarios don't have a clear natural end. Think of a robot continuously collecting trash in a factory, or a system managing climate control in a building indefinitely. These are continuing tasks.
Right. They just keep going.
If we just sum rewards indefinitely, the return could theoretically be infinite, which isn't helpful for learning.
True.
So for continuing tasks, we introduce a crucial element, a discount rate, gamma, a value between 0 and 1.
Okay.
This discount rate effectively makes future rewards worth less than immediate ones. The return then becomes an infinite sum. GT on RT plus 1 plus ANS plus 2 plus chord plus 3 plus eddy.
So it's weighted.
This means rewards received sooner are weighted more heavily, preventing infinite sums and making long-term planning mathematically tractable. It also reflects a common intuition. $1 today is worth more than $1 tomorrow.
Makes sense.
We can actually use a unified notation for both episodic and continuing tasks by imagining an absorbing state at the end of an episode, which always transitions to itself with 0 reward, effectively making episodic tasks a special case of continuing tasks.
Okay, so we've got the agent, the environment, actions, states, and the crucial concept of maximizing cumulative return. But how does the agent actually keep track of what's working and what's not? What are the internal tools or thought processes it develops to navigate this complex goal?
That leads us to 2 truly essential internal elements, policies and value functions.
Policies and value functions.
First, a policy denoted by the abatai is the agent's decision-making role. It's essentially a mapping from states to actions, telling the agent what to do in any given situation.
Like its strategy.
Exactly. A policy can be deterministic, meaning it always takes one specific action in a given state, or it could be stochastic, meaning it chooses actions with certain probabilities.
Right.
You can think of it as the agent's complete strategy or behavior.
So the policy is the how-to guide for the agent, and then there are these value functions. I've heard that term before. How do they relate to the policy, and why are they so important?
Value functions are the agent's internal compass for how good things are. They are crucial because they provide estimates of how good it is to be in a particular state or to take a specific action in a state in terms of the expected future rewards, those returns we just discussed, that will follow.
Ah, okay, the long-term score.
It's the ultimate scorekeeping mechanism, telling the agent the long-term potential of being in a particular state or of taking a specific action from that state. Without this compass, the agent would be utterly lost, just making random moves.
Right.
We have two main types. The state value function, VAS, which is the expected return starting from state and then consistently following policy.
Okay,
And the action value function, QSA, which is the expected return starting from state SA, taking a specific action A and then following policy.
got it.
These are the predictions of future reward. And the agent's goal is to learn them as accurately as possible.
So if I'm playing checkers, the state value function tells me how strong my current board position is, and the action value function tells me how good making a specific move from this position would be in terms of eventually winning the game.
Perfectly put. Yeah.
That makes so much sense. And for these functions to work well, there's often something called the Markov property involved, right?
Exactly right. For these value functions to be truly robust and efficient, we ideally want the state signal to have what's called the Markov property.
The Markov property.
This means that a state should compactly summarize all relevant information from the past, retaining everything necessary to predict the future. If an environment state signal has this property, we call it a Markov decision process, or MDP. The checkers board you mentioned is a classic example. The current configuration of all pieces on the board contains all the necessary information for the rest of the game, regardless of how the pieces got there. You don't need to know the history of moves, just the current board is enough.
But what about more complex real-world situations, like a high-stakes game of poker, where an opponent's betting history or even their subtle tells might actually matter? It seems like a single state wouldn't capture everything there.
That's a great nuance, and it highlights a very practical point. In many real-world scenarios, obtaining a perfectly Markov state might be impossible or simply too complex to compute.
Yeah, that seems likely.
In poker, observing an opponent's past betting patterns or even subtle facial expressions can indeed influence your decisions. A truly perfect Markov state would need to include all of that, which is often infeasible for an AI.
Right.
However, what's fascinating here is that even with non-Markov states, states that don't capture absolutely everything, agents can still learn to make very good, often excellent decisions.
Oh, interesting.
The state representation humans use in poker is undoubtedly non-Markov, yet we make complex decisions. It means that while the Markov property is an ideal for theoretical guarantees, its absence isn't necessarily a severe problem for an RL agent in practice. Often, a sufficient state representation is enough.
That's a relief to hear. So the ultimate goal then is to find the best possible values, the absolute peak performance.
Precisely. Our aim is to discover the optimal value functions, denoted VS and QSA.
V star and Q star.
These represent the maximum possible expected return achievable from any given state or any state action pair, respectively, if the agent were following an optimal policy.
Pi star, the best strategy.
The entire purpose, the holy grail of many RL algorithms, is to discover these optimal value functions, which then implicitly tell the agent the best possible policy to follow in every situation.
This raises an important question that feels like a fundamental dilemma. If an agent needs to explore its environment to discover new, potentially better actions, but it also needs to exploit what it already knows is good to maximize its immediate rewards, isn't there a fundamental conflict there?
Yes.
How does an AI balance those two desires?
You've hit on perhaps one of the most distinctive and challenging aspects of reinforcement learning, the exploration-exploitation dilemma.
Explore versus exploit.
To get a lot of reward, an agent must exploit actions it already knows are good, sticking with what's proven to be effective. But crucially, to discover even better actions or to adapt to changing environments, it must explore new, untried possibilities.
You can't just do one.
Neither strategy can be pursued exclusively without eventually failing at the task.
You know, it makes me think about trying a new restaurant. Do I stick with my favorite dish I know is good, or do I try that intriguing new special that might be amazing or might be a disaster?
That's a perfect analogy.
That's the tension our AI faces, isn't it?
A perfect analogy. If you only exploit, you might never discover a truly outstanding new dish. If you only explore, you might have a string of terrible meals.
Exactly.
We can illustrate this vividly with a classic problem called the N-armed bandit problem. Imagine you're at a row of N different slot machines, or one-armed bandits.
Okay.
Each time you pull a lever, you get a reward drawn from a fixed but unknown probability distribution specific to that machine. Your goal is to maximize your total winnings over, say, 1,000 pulls. You don't know which machine pays out the most on average.
So you literally have to try them out to figure out their average payout.
Exactly. If you somehow knew the true value, the expected reward of each action beforehand, you'd simply always pick the best one. But since you don't, you have to estimate. The simplest approach is often a purely greedy strategy. Always pick the action with the highest estimated value based on the data you've collected so far.
Just go for the current best guess.
Yeah. However, as our source material graphically illustrates, a greedy method on a 10-armed test bed quickly plateaus at a lower average reward. Why? Because if its early samples for a truly optimal action were misleadingly low, it gets stuck on a suboptimal choice, never realizing there's a better one out there.
It stops exploring too soon.
It only manages to find the optimal action in about 1/3 of tasks, which isn't great.
So it's not exploring enough. How do we build in that crucial element of discovery?
A very common, elegant, and simple approach is greedy. Epsilon greedy.
Epsilon greedy. Okay.
With a small probability, epsilon, the agent chooses a random action. That's the exploration part.
Just try something random.
Otherwise, with probability 1a, it chooses the greedy action, the one it currently believes to be best. That's the exploitation part.
Mostly exploit, sometimes explore.
Exactly. And the source material beautifully demonstrates the advantage. Greedy methods, like those with ABO.1 or ECME.01, improve more slowly initially because of the random choices, but they ultimately achieve significantly higher average rewards and find the optimal action much more frequently.
So they eventually find the better machine.
They continuously explore, allowing them to eventually converge on the true best action. The AB.01 method, while slower to rise, often performs even better than AB.1 in the very long run because it explores less randomly once its estimates are fairly good.
That's a powerful insight. A small, calculated risk of a random choice pays off immensely in the long run by discovering better options.
Indeed. This balance is absolutely crucial, especially in non-stationary environments where the optimal actions might change over time.
Right, if the world changes.
If the best slot machine's payout distribution changes, continuous exploration is necessary to detect that shift and adapt. The core idea is that reinforcement learning inherently creates an effectively non-stationary problem, because as our value estimates change and improve, what constitutes the greedy action also changes, meaning new information is always valuable. This dilemma is a distinctive challenge that every RL algorithm must address.
All right, we've firmly established the foundational concepts of reinforcement learning. We understand the agent, the environment, rewards, policies, and the crucial exploration-exploitation balance. Now, let's turn our attention to the first family of algorithms designed to solve these problems: dynamic programming, or DP.
Okay, DP.
When I hear dynamic programming, I typically think of breaking down a large, complex problem into smaller, more manageable subproblems. Is that the core idea at play here in RL?
That's a great intuition, and it certainly resonates with the broader computer science definition of DP.
Yeah.
But in the context of reinforcement learning, the core idea of DP is a bit more specific and, frankly, quite powerful, though with a critical caveat.
Okay, what's the caveat?
DP refers to a collection of algorithms that can compute optimal policies for finite Markov decision processes, MDPs. The key distinction, and you really can't overstate its importance, is that DP methods require a perfect model of the environment's dynamics.
What perfect model? Wow.
This means you must know exactly how the environment will respond to every action from every state, including the precise probabilities of transitioning to new states and the exact rewards you'll receive.
So you need the rule book, the complete rule book.
Exactly. It's essentially about planning, deciding on an optimal course of action by meticulously considering all possible future situations before they are actually experienced.
So if I had an absolutely complete and accurate instruction manual for a game like chess detailing every possible move and its outcome, then DP could theoretically compute the best strategy.
Exactly. It's fundamentally model-based.
Yeah.
Without that complete and accurate model, DP simply cannot work in its classical form.
Gotcha. Model-based.
Another fundamental concept central to DP, and indeed to many other RL algorithms we'll discuss, is bootstrapping.
Bootstrapping. Okay.
It sounds a bit like pulling yourself up by your own shoelaces, and in a way, it is.
Ha.
Imagine you're trying to budget for a complex, multi-year project. You don't know the final cost yet. So you estimate the cost of the first phase, and then you add your current best estimate for the second phase, and then your current best estimate for the third, and so on.
You're using guesses to make better guesses.
You're building an estimate using other estimates you already have, rather than waiting for all the concrete final numbers. That's bootstrapping in action, a powerful shortcut. Updating estimates based on other estimates, especially useful when a perfect model is available.
Okay, so DP needs a perfect map, and it uses its current best guesses to refine other guesses. How do these powerful DP algorithms actually work in practice to find an optimal policy?
DP algorithms typically involve an iterative process that alternates between two main conceptually simple steps: policy evaluation and policy improvement.
Okay, evaluation and improvement. Let's delve into policy evaluation first.
Policy evaluation answers a very specific question. Given a particular policy, our current strategy, how good is it? How do we compute its associated value function, V?
So grading the current plan.
Exactly. It's an iterative process. You start with an arbitrary guess for your value function for all states. Then you repeatedly apply the Bellman equation for V. It's an update rule.
The Bellman equation.
Essentially, for each state, you look at all possible actions prescribed by your current policy, consider the immediate reward you expect, and average in the discounted value of the next states based on your current estimates of those next states.
Okay, using those bootstrapped estimates?
You do this over and over, propagating value information throughout the state space until the value function stabilizes and converges to the true V. A common practical technique is to update values in place, meaning you use a single array to store the values and overwrite them as soon as new ones are computed, which often leads to faster convergence.
So once we have a solid estimate of how good our current policy is, our V, how do we use that information to make our policy better?
That's where policy improvement comes in. Once you have a sufficiently accurate estimate of V, you can improve your policy by making it greedy with respect to V.
Going greedy.
For each state, you simply consider all possible actions you could take from that state. For each action, you calculate what immediate reward you'd get, plus the discounted value of the next state you'd end up in, according to your V estimates.
Yeah, I do.
Then you choose the action that leads to the best expected next outcome. If taking action A leads to a state with an estimated value of 10 and action B leads to a state with an estimated value of 5, you'd greedily choose A.
Straightforward enough. Choose the best-looking move based on current values.
Exactly.
And these two steps, evaluation and improvement, work together in a cycle that's called policy iteration.
Precisely. Policy iteration cleverly combines these two phases. You start with an arbitrary policy, say over a 0.
Okay.
Then you enter a cycle. First, you fully evaluate via computing the state values for your current policy FIC. Second, you improve FIC to get via +1 by making it greedy with respect to via. You repeat this cycle until the policy no longer changes, meaning you've found an optimal policy.
And it's guaranteed to find the best one.
Guaranteed to converge to an optimal policy and optimal value function. What's truly fascinating here, as the source material illustrates, is that for relatively simple tasks like a grid world maze, policy iteration can find an optimal policy in surprisingly few iterations, sometimes even just one.
Wow, that's fast.
It's incredibly efficient at quickly identifying that shortest path to a goal once it has a model.
Policy iteration sounds thorough, taking its time to fully evaluate a policy before making an improvement. But if we're in a hurry, is there a way to speed up that process, perhaps by not waiting for full convergence at each evaluation step?
Indeed. That brings us to value iteration. This is a simplified, often faster version of policy iteration that doesn't wait for the policy evaluation step to fully converge.
Okay, a shortcut.
Instead, it directly updates the values based on the Bellman optimality equation, which crucially includes a max over actions within the update itself. The update rule is VK plus 1, Farshas max is max a year plus 1 plus cow, chauti plus 1 STS, edia.
So it combines the steps.
You can conceptualize it as essentially combining a truncated one-step policy evaluation with a policy improvement step into a single compact update. It's still bootstrapping, still model-based, but more aggressive.
Could you give us a concrete example of value iteration in action where we can see this iterative refinement?
The gambler's problem is a fantastic illustration. Imagine a gambler who starts with some amount of capital and on each turn bets a portion of it on a coin flip. The goal is to reach $100 before running out of money.
High stakes.
The actions available are how much to stake on each flip, Value iteration iteratively refines the optimal value function, how good it is to have, say, $50, and then implicitly the optimal policy. What's the best stake to make, given your current capital to most efficiently reach $100?
So it figures out the best betting strategy.
What value iteration reveals here isn't just a calculation, it's a profound insight into dynamic risk management.
Hmm.
It's figuring out, moment by moment, the optimal balance of aggression and caution to reach a distant, uncertain goal.
Hmm.
It effectively calculates the smartest way to manage risk and reward over time, almost like a real-time financial planner for your AI.
DP sounds incredibly powerful for planning if you have a perfect model, almost like an omniscient game master. But there must be downsides, right? This kind of detailed calculation seems like it would hit a wall quickly.
You've hit on its biggest, most infamous limitation, the curse of dimensionality.
Ah, the curse.
Classical DP methods, in their pure form, require computation and memory for every single state in the environment. The computational requirements grow exponentially with the number of state variables.
Exponentially. That's bad.
Bellman himself coined the term curse of dimensionality to describe this daunting problem. For problems with even moderately large state spaces, like chess, which has about 143 possible positions,
Whoa.
or even more so for continuous control problems like robotics, or especially complex logistical systems like elevator dispatching, which can have upwards of 1022 states, classical DP methods become utterly unfeasible.
Just way too many states.
You just can't store or compute values for that many states in any reasonable amount of time or memory.
So for most truly interesting real-world problems, we can't compute optimal policies directly using DP. It's too slow, too memory-intensive.
Exactly.
That means we have to approximate them.
Precisely. This fundamental limitation is what drives the development of other, more advanced reinforcement learning methods that learn from actual experience and can generalize across states, rather than needing to explicitly visit and value every single one. DP is brilliant for theory and smaller problems, but for the grand challenges, we need a different approach.
That's a perfect segue because if dynamic programming is about planning with a perfect map, a comprehensive blueprint of the world, what if we don't have that map?
Right.
What if we're thrown into a completely new environment, like a foreign city, and have to figure things out through pure trial and error, purely from direct experience?
That's exactly where Monte Carlo MC methods come into play.
Mm.
The core idea here is fundamentally different and incredibly liberating compared to DP. Monte Carlo methods are model-free.
Model-free. Okay, that's the key difference.
They don't require any prior knowledge of the environment's dynamics. No transition probabilities, no explicit reward functions provided beforehand. Instead, they learn optimal behavior directly from experience, specifically from complete sample sequences of states, actions, and rewards that come from actual or simulated interaction with an environment.
So no map needed, just raw, direct experience. How do they actually achieve that learning without a model?
MC methods work by a very simple yet powerful principle. Averaging the actual returns, those cumulative rewards we discussed earlier, observed following each stake or each state action pair over many complete episodes.
Averaging the real outcomes.
Unlike DP, which bootstraps, updates estimates based on other estimates, MC methods typically wait until the end of an entire episode to know the full true return for each state or action that occurred within that episode.
So no bootstrapping during the episode.
They use the true observed return, not an estimate of a future state's value. This means they don't bootstrap within an episode. They need to see the whole story unfold.
Okay, so they need full episodes to calculate values. How do these MC algorithms actually work to estimate values or find policies?
Let's consider how they estimate value functions, which is known as MC for policy evaluation. There are two main flavors, first visit MC and every visit MC.
First visit versus every visit.
First visit MC estimates the value of a state S as the average of the returns observed only after the first time MC is visited in each episode. This is the most widely studied version.
Okay.
Every visit MC, on the other hand, averages returns following all visits to S within an episode.
Got it. Two ways to average.
The principle is elegantly simple. To estimate VN for a given policy, you just collect many episodes by following that policy. For every state S encountered in an episode, you record the total return, GT, that followed it. Then you average these returns across all episodes where S was visited, using either the first visit or every visit rule.
Keep running episodes and average the scores.
As the number of visits approaches infinity, These averages are mathematically guaranteed to converge to the true value V. It's like running a scientific experiment many times and averaging the results.
And how about using Monte Carlo to find an optimal policy, not just evaluate an existing one? So Monte Carlo for control.
For that, we extended to MC for control, using the same generalized policy iteration GPI framework we saw in DT, which means alternating between evaluation and improvement.
GPI again. Evaluate, improve, repeat.
Monte Carlo methods are particularly well suited for estimating action value functions, QSA. Why action value functions? Because to improve a policy without a model of the environment, you absolutely need to know the value of each action in each state.
Ah, right. Need action values if you don't have the model.
If you only had state values, you wouldn't know which action to take to get to the good successor states unless you had a model of the transitions. With action values, you can directly choose the action that has the highest estimated value from any given state, thus directly improving your policy.
So policy improvement is simply picking the best action based on these action values.
Exactly. You make the policy greedy with respect to the current action value estimates. SEAL, argmaxa, QSS.
Go greedy on the Q values.
This iterative process of evaluating QUK and then making QUK plus one greedy with respect to it is also guaranteed to converge to an optimal policy and optimal action value function. This is truly remarkable. MC methods can find optimal policies using only sample episodes, with no prior knowledge of the environment's internal workings.
That's quite powerful, learning an optimal policy purely from samples, without a model. But expert, what about the blind spots? If we only learn from experience, how do we know we haven't missed an even better path because our initial explorations were limited, or because we're trying to learn about an optimal policy while still needing to explore? Does Monte Carlo have a way to handle that persistent uncertainty, to learn about one policy while behaving differently?
That's a crucial, astute observation, and it leads us directly to a more advanced concept, off-policy learning with important sampling.
Off-policy learning, important sampling. Okay.
The challenge you describe arises when you want to learn about a specific target policy. Perhaps the theoretically optimal, purely greedy policy, while simultaneously following a more exploratory behavior policy to ensure you gather enough diverse experiences and don't get stuck.
So learning about policy A while acting according to policy B.
Exactly. If the behavior policy is more likely to take certain actions than the target policy would, or vice versa, then the observed returns from the behavior policy won't directly represent the target policy's performance. It's like trying to learn the best way to drive a race car by observing someone driving a family sedan. The experiences don't quite match.
So we need a way to correct for that difference in how the data was generated versus what we want to learn about.
Precisely. Importance sampling is a clever statistical technique that does exactly this. It corrects for the difference by weighting the observed returns from the behavior policy.
Weighting the returns.
The weight is calculated as the ratio of the probabilities of a particular sequence of actions, a trajectory, occurring under the target policy versus under the behavior policy.
Okay, a probability ratio.
If the behavior policy made an action much less likely than the target policy would have, but that action led to a good outcome, importance sampling scales up the credit for that outcome, giving it more influence on the target policy's value estimate.
Is there a preferred way to do this weighting to make it stable? I imagine those ratios could get crazy.
Yes, that's a key point. There's ordinary importance sampling and weighted importance sampling. Our sources point out that while ordinary importance sampling is mathematically unbiased, meaning it's correct on average, its variance can be unbounded, meaning its estimates can be wildly inaccurate from one sample to the next, making it unstable.
Unstable is bad.
In contrast, weighted importance sampling typically has much lower variance and is therefore strongly preferred in practice. It achieves this by normalizing the weights, ensuring that the largest weight on any single return is 1, which prevents extreme scaling and keeps the estimates more stable.
Weighted importance sampling. Okay, the practical choice. Can you give us a concrete example where this off-policy learning with importance sampling really shines?
Absolutely. Think of the game of blackjack. You want to learn the optimal strategy for playing blackjack, meaning the exact value of a specific state, like having a total 13 when you have a usable ace, a soft 13, and the dealer is showing a deuce.
Okay, specific scenario.
The target policy you want to learn about might be a very strict optimal one, like stick on 20 or 21, hit otherwise. But to learn efficiently, especially in the early stages, you might use a behavior policy that randomly hits or sticks.
Explore randomly, learn optimally.
Monte Carlo, with weighted importance sampling, can be used to estimate the value of that specific soft 13 versus do state, from data generated by your random behavior policy. As the source material vividly shows, weighted importance sampling significantly outperforms ordinary importance sampling in terms of error, closely approximating the true value even from limited off-policy data, essentially allowing you to learn the best strategy even while you're still exploring.
So to sum up, what are the big takeaways from Monte Carlo methods? What are their main advantages and limitations?
The primary advantages of Monte Carlo methods are indeed powerful. 1. Model-free. This is their standout feature. They learn directly from experience, so no explicit environment model is needed. This is incredibly valuable for complex or unknown environments. Huge plus. Sample-based. They can be used with simulated models that only generate samples, not full probability distributions. You just need to be able to run a simulation. 3. Focused learning. It's often efficient to focus Monte Carlo methods on evaluating or improving a small subset of states without evaluating the entire state space, which is a major advantage over DP for large problems.
Good for big problems then. But what about the downsides?
However, they do come with significant limitations. 1. Requires episodes. Monte Carlo methods need to wait until the end of an entire episode to perform updates. This can make learning quite slow if episodes are very long, or if the agent rarely reaches a terminal state.
The waiting game.
Imagine a robot that takes days to complete a task. It would only learn after days.
Yeah, not ideal.
High variance. Because they rely on full, potentially long and noisy returns, the updates can have high variance. Individual experiences might be quite misleading due to a sequence of unlikely events, making the learning process less stable.
So the results can jump around a lot.
Exactly.
It certainly sounds like a powerful tool for learning without a model, a true trial and error master, but that waiting until the end of the episode bit could definitely be a significant bottleneck in many real-world scenarios.
Exactly. That bottleneck, the need to wait for an entire episode to conclude, is precisely what temporal difference, or TD learning, aims to solve.
Ah, the solution.
If we had to pinpoint one idea that is considered central and truly novel to reinforcement learning, it would undoubtedly be TD learning. It represents a breakthrough in how agents can learn efficiently.
Here's where it gets really interesting, though. How does TD learning manage to bridge that crucial gap between Monte Carlo's direct experience and dynamic programming's internal model-based estimates? What's its secret?
The big idea is that TD learning is a truly fascinating hybrid. Like Monte Carlo methods, TD methods are model-free. They can learn directly from raw experience without needing an explicit model of the environment's dynamics.
Okay, model-free like MC.
No prior blueprints required. But critically, like dynamic programming TD methods bootstrap, they update estimates based in part on other learned estimates, rather than waiting for a final, complete outcome.
Bootstrapping like DP. Okay, interesting mix.
They perform updates more frequently. They get their name from the temporal difference. They are driven by the difference between temporally successive estimates of the same quantity.
So it's almost like it gets the best of both worlds. Learning without a model, but updating much more frequently and incrementally than Monte Carlo.
In many practical applications, that's precisely the case. And it's a huge advantage. Let's look at the simplest and most fundamental TD method, TD0.
TD0.
Recall that a constant alpha Monte Carlo method updates its value estimate for a state, vsaint, using GANA, the actual total return, which is only known at the very end of an episode.
Right, the full return.
TD0, however, only needs to wait until the next time step to make an update.
Just one step. Wow. So how does that immediate one-step update actually work? What's the mechanism?
Okay, let's get to the mechanics.
Yeah.
Forget the formula for a second. Imagine you're on a long road trip, and you estimate it will take 8 hours to reach your destination.
Okay, I'm driving.
As you drive for an hour, you get an immediate piece of information, the reward of driving for a bit, say manage 1 hour, and you also form a new, updated estimate of how much time is left from your current position.
I see traffic. I revise my estimate.
TD0 does exactly that, saying, my current guess for the value of this state stent should be adjusted based on the immediate reward, right, plus 1 I just got, plus my best guess, my estimated value, of the very next state, VN cent plus 1.
Use the immediate reward plus the guess for the next state.
So it's always looking just one step ahead, getting immediate feedback, and revising its current prediction. Now, the actual update rule, when we write it out, looks like this. vcent plus I delta t plus 1 plus given sant plus 1. Okay, let's break down that formula a bit. The right plus 1 plus mods, the sant plus 1 part is the TD target, right?
Exactly. That whole term, art plus 1 plus v sant plus 1, is called the TD target. It's an estimate of the true return, but it's built from two immediate pieces of information. the observed immediate reward, R+1, and the estimated value of the very next state, Vn+1.
The bootstrapping part. This Vn plus 1 is the crucial bootstrapping part. We're using an existing estimate of a future state's value rather than waiting for the entire actual return of the episode.
Got it.
The P part is what we call the temporal difference error, essentially.
Right.
How much our current estimate of VS deviates from this new bootstrapped one-step target. It's the surprise or correction signal that drives learning.
So instead of waiting for the full journey to complete, it just looks one step ahead, gets immediate feedback, and adjusts its current estimate based on what it thinks the next state is worth. That truly is incremental.
It is indeed. To quickly compare the targets, the Monte Carlo target, GT, is an unbiased estimate of the true return, but requires waiting for the episode's end.
Right.
The dynamic programming target, +1 plus SAN plus 1, uses a full model, is also bootstrapped, and relies on expected values.
Okay.
The TD target, on the other hand, is an estimate for both reasons. It samples the expected values, since ρ+1 and SAN plus 1 are samples from the environment, and it uses existing estimates to bootstrap.
Sampling and bootstrapping.
The backup diagram for TD0 visualizes this difference beautifully, showing an update based on a single sample transition to the immediately following state, unlike DP's sweeping full backups.
This sounds incredibly intuitive and practical. What are the main advantages that this online incremental learning offers?
That's one of the biggest advantages of TD0. It allows for truly incremental online learning, updating its estimates after every single step without needing to wait for episode completion.
Learn as you go.
This means it can learn continuously, even from incomplete episodes, which is absolutely critical for continuing tasks or very long episodes that might never formally terminate.
Handles continuing tasks well.
In practice, TD methods often converge faster than constant alpha Monte Carlo methods, especially on stochastic tasks where there's a lot of randomness. The random walk example vividly illustrates this. TD0 generally performs much better than MC in predicting state values because it makes updates more frequently and with potentially more stable, less noisy targets.
So TD0 is fantastic for prediction, for estimating the value of states. But how do we use this powerful approach to actually control an agent, meaning finding an optimal policy, deciding what actions to take?
Just as with DP and MC, we extend TD methods to control by wrapping them within the Generalized Policy Iteration GPI framework.
GPI again. That pattern keeps coming back.
This often involves estimating action value functions, or Q values, because knowing the value of taking a specific action from a state allows us to directly choose the best action. This brings us to two incredibly important and widely used TD control methods, SARSA and Q-learning.
SARSA and Q-learning. Okay, the big two. Let's start with SARSA. What's the story behind that name and how does it work?
SARSA is an on-policy TD control method. Its update rule is Q ascent at Q ascent at plus IR8 plus 1 plus dust plus 1 at plus 1 at Q ascent at actually.
Looks similar to TD0 but with Q values.
The name SARSA isn't an acronym in the traditional sense, but it cleverly comes from the sequence of events it uses for its update. You observe the state, take an action, receive a reward, land in a new state, and then take the next action from there.
SARSA. Okay, makes sense.
The key insight is that the update uses the next action, at +1, that is actually taken by the agent according to its current policy.
The one it actually did.
Because it learns the value function for the policy it is currently following, including any exploratory actions it makes. It is inherently an on-policy method. It learns to evaluate the very strategy it's using, warts and all.
So SARSA is essentially learning the value of its current, often exploring behavior. Can you give us an example where this characteristic is particularly important?
Absolutely. The windy grid world example beautifully illustrates SARSA. Imagine a grid world maze where some columns have an upward wind that pushes the agent.
Annoying wind.
If the agent makes a greedy move that brings it close to a windy edge, its subsequent exploratory actions might push it off the grid, resulting in a penalty. SARSA, being on policy, accounts for this risk.
It learns about the danger of its own randomness.
It learns a safe path to the goal, often a longer one, but one that avoids areas where the wind combined with its exploratory actions might lead to disaster. It learns step by step and quickly adapts away from poor policies because its evaluation includes the consequences of its own exploratory steps.
Interesting. So it's conservative.
Monte Carlo methods would struggle here because termination isn't guaranteed for all policies, meaning an episode might never end if the agent gets stuck by the wind.
That's a powerful distinction, learning a safe path rather than just the shortest. And what about Q learning? I understand that's an off-policy method, which means something quite different.
Yes, Q-learning is a seminal off-policy TD control method, and it introduces a subtle but incredibly powerful change. Its update rule is QSN et not, plus are you right, +1 plus Kappa Q, isane +1 8 point.
Okay, I see the difference. Maxa instead of the actual next action.
The crucial difference compared to SARSA lies in the target. Instead of using QST +1 at +1, the value of the actually taken next action Q-learning uses maxa Q ST +1 A.
The best possible value from the next state.
This means it always considers the maximum possible Q value for the next state, effectively assuming the best possible action will be taken from the next state, regardless of what the agent actually does.
So it learns about the optimal policy even while the agent itself is still flailing around and exploring inefficiently, taking non-optimal actions.
Exactly. This is the brilliance of off-policy learning. Q-learning learns the value of the optimal policy independent of the behavior policy currently being followed for exploration. Example, an ORDI policy.
Wow, that seems very useful.
This means it can effectively separate the act of exploration from the learning of the optimal strategy. The cliff walking example perfectly demonstrates this distinction between SARSA and Q-learning.
The cliff walker.
In this task, there's a cliff that gives a large negative reward if entered. SARSA, on policy, learns a safe path that skirts around the cliff, often taking a longer route, because its policy considers the risk of falling even during exploration.
Like the windy grid world. Safety first.
Q-learning, off policy, however, learns the optimal path to the goal, which is often the shortest path, and runs right along the dangerous cliff edge.
Takes the risky but faster route.
It learns this optimal path because it always considers the maximal future reward, the ideal scenario, regardless of how it got there. If the optimal path means getting dangerously close to an area where exploratory actions might cause a fall, SARSA would avoid it to be safe, while Q-learning would still aim for that optimal path, learning its true maximal value.
That's a truly powerful distinction, learning the truly optimal path versus learning a safe path under exploration. And I remember you briefly mentioned afterstates earlier. How do they fit into these TD control methods?
Ah, yes, afterstates.
Yeah.
What's fascinating here is that in tasks like games, e.g. tic-tac-toe, backgammon, or even industrial control, we can make these methods even more efficient by using afterstates.
Afterstates.
An afterstate is a position after the agent has made its deterministic move, but before the environment responds with any stochastic random outcomes.
So the state after my move, but before the dice roll, for example.
Exactly. In games, for instance, when you make a move, you know the immediate resulting board configuration. Using afterstates allows it to evaluate the resulting board position directly, rather than having to separately evaluate every position move pair that might lead to the same identical outcome.
Reduces computation.
This significantly reduces redundant calculations and can speed up learning, making these complex tasks more tractable for AI.
We've now explored dynamic programming with its precise planning given a perfect model, Monte Carlo's robust model-free trial and error, and the brilliant hybrid that is temporal difference learning with TD0, SARSA, and Q-learning. Now we're going to dive into an even more sophisticated fusion, TD, which introduces a concept called eligibility traces.
Ah, TD lambda.
Yes. This sounds like it could be the ultimate bridge between all these foundational ideas.
It absolutely is, and it's one of the most powerful and elegant ideas in reinforcement learning, truly unifying TD and Monte Carlo methods along a continuous spectrum.
A spectrum, okay.
The idea actually starts with n-step TD methods. The question here is, what if we don't just look one step ahead, like TD0, or all the way to the end of the episode, like Monte Carlo, but somewhere intelligently in between?
So a compromise, like looking 2 steps ahead, or 3 or 10.
Exactly. An n-step method bases its update on the first n rewards observed from a state, and then the estimated value of the state n steps later.
Okay, look n steps out.
If n1, it's purely TD0. If n is large enough to encompass the entire episode, it effectively becomes Monte Carlo, waiting until the end. This approach creates a continuous spectrum of methods moving from very short-term prediction to very long-term.
The n controls the horizon.
What's compelling, and the source material illustrates this for a larger random walk process, is that intermediate values of n can often perform significantly better than either extreme.
The sweet spot in the middle.
It's like having neither perfect foresight nor perfect short-sightedness, but a balanced view.
That makes sense. Too short-sighted, and you miss big opportunities. Too long-sighted, and the future is too noisy and uncertain. So instead of picking a single n for this balance, could we somehow average all these n-step possibilities in a clever way?
That's precisely the brilliance of TD. This is known as the forward view of TD. Instead of choosing a single n, TD computes a return, which is an exponentially weighted average of all possible n-step returns.
Lambda return. Okay, averaging all n-steps.
The parameter, lambda, a value between 0 and 1, is the dial that controls this weighting.
How does that weighting work? How does Laro influence the blend?
Think of arrow as a fading memory or an attention span. The one-step return gets the largest weight, 1, because it's the most immediate and certain.
Right.
The two-step return gets a slightly smaller weight, 1, 1. The three-step return gets an even smaller weight, 1 layer, and so on. The weight decays exponentially by Seuss for each additional step further into the future.
So later steps count less and less, controlled by lambda.
Exactly, as beautifully illustrated in the source material.
What does that allo signify intuitively? How does it relate to TD0 and Monte Carlo?
It's essentially a dial or a sliding scale between pure TD and pure Monte Carlo. If EO0, the arrow effectively considers only the one-step return, making TD mathematically equivalent to TD0. All its attention is on the immediate next step.
Lambda 0 is TD0.
If EP equals 1, the return becomes the full Monte Carlo return, GET, effectively making TD equivalent to a constant alpha Monte Carlo method. It waits to see the entire outcome.
Lambda 1 is Monte Carlo.
The backup diagram for TD visually shows how it gracefully combines information from various future time steps, like a cascade of information. This elegant, continuous interpolation between pure TD and pure Monte Carlo is incredibly powerful, and in practice it often leads to significantly faster learning and better performance by allowing the algorithm to dynamically choose its horizon of learning.
That's the theoretical forward view, which elegantly looks into the future to calculate this weighted average. But expert, that implies we can somehow glimpse into the future to make our calculations. In the real world, we don't have a crystal ball.
Right, right.
What's the practical challenge here, and how do we overcome that limitation for real-time online learning?
You've spotted the crucial practical limitation. The forward view is indeed theoretical and a causal because it requires knowing future rewards and states to calculate the return, which simply isn't practical for real-time online updates as an agent interacts with this environment.
Can't look into the future.
This is where the true engineering genius comes in, the backward view of TD. This view provides a completely causal, mechanistic way to approximate the forward view. And in specific offline cases where updates are only made at the end of an episode, it can even achieve it exactly.
The backward view. Okay, and this backward view uses something called eligibility traces. That sounds like a fascinating concept.
Yes, eligibility traces are the secret sauce here. They're the mechanistic heart of the backward view.
Eligibility traces.
Eligibility traces are a short-term memory vector, one for each state or state action pair, that records how eligible or responsible that state or action is for receiving learning credit when a surprise, a TD error, occurs.
So keeping track of which states deserve credit or blame.
Think of it like a temporary highlighter that marks how recently and frequently a state or action has been involved in the agent's recent trajectory.
How do these traces actually work? How do they keep track of eligibility?
When a state is visited, its eligibility trace is immediately incremented, or set to 1. Then, at each subsequent time step, all traces for all states decay over time, multiplied by Gay.
Decay over time.
This dual action means that recently visited states retain higher eligibility traces, while older ones gradually fade away, reflecting their diminishing responsibility for current events.
Memory fades.
This trace acts as a dynamic memory of past states. At each step, we calculate the TD error, which is our immediate surprise. There was isolate +1, +1, +1, the surprise signal.
This error, this surprise or correction signal, is then shouted back to all previous states or actions proportional to their current eligibility trace. Shouted back! I love that imagery. So previous states that contributed to the current situation that led to this surprise get a share of the credit or blame, depending on how recently they were visited.
Exactly. The update rule is WT plus 1 is distributed back to all states or actions that had an eligibility trace at that moment. States visited more recently and frequently receive a larger share of the credit or blame for the current TD error.
Spreading the learning back through time.
The source material visualizes this shouting back of the error signal, propagating backward in time along the traces, effectively connecting the current surprise to its causal history. This is a remarkably efficient way to distribute credit and blame across many steps without having to wait until the end of an episode or store all past experiences.
Are there different flavors of eligibility traces or different ways they can behave?
Yes, the source mentions a few types, reflecting different ways to manage that memory. The most common is accumulating traces, which simply add one each time a state is visited and then decay.
Accumulating. Okay.
Then there are replacing traces, where a state's trace is reset to 1 each time it's visited, rather than incrementing and then decays. This can be particularly beneficial, especially when combining with function approximation.
Replacing traces. Reset to 1.
Finally, there are Dutch traces, which offer a hybrid form. What's crucial to understand for practical purposes is that in an offline learning scenario where updates are made only at the end of an episode, the backward view with accumulating traces exactly reproduces the forward view of TD.
Ah, they match offline.
For online learning, which is what we usually want, it's a very close and highly practical approximation.
So we can naturally extend SARSA and Q learning, our TD control methods, to use these eligibility
Yeah,
traces.
absolutely. That brings us to SARSA and Q, which are the trace-enhanced versions of our earlier TD control methods.
SARSA lambda and Q lambda.
ARSA extends our on-policy SARSA method to incorporate eligibility traces. This allows the TD error to be propagated over multiple steps, giving credit not just to the immediately preceding action, but also to earlier actions in a sequence that ultimately led to a reward or penalty.
Spreads credit further back.
This distribution of credit over time significantly speeds up learning. For instance, in a grid world path example, one-step SARSA only strengthens the last action taken just before reward. SARSA, with a higher, like 0.9, strengthens many actions along the path leading to that reward, with the strength diminishing with distance from the reward, making learning much, much faster.
That's a huge difference. And what about Q learning with traces for off-policy learning?
That's Watkins Q. This is an off-policy TD control method. A key characteristic here is that the eligibility traces are immediately set to 0. They are cut off whenever an exploratory, non-greedy action is taken.
Cut off the trace. Why?
This ensures that the updates, which are trying to learn the optimal greedy policy, remain consistent and are always directed toward that optimal policy, even if the agent deviates for exploration.
Ah, to keep it focused on the optimal path despite exploration.
However, this trace cutoff can sometimes significantly reduce the speed-up benefits of eligibility traces, especially if exploration is frequent, as it effectively limits the multi-step propagation of credit for those exploratory actions. It's a trade-off between theoretical soundness for off-policy learning and the practical efficiency of traces.
Interesting trade-off there. This sounds incredibly sophisticated and like a lot of intricate moving parts working together. Has this kind of algorithm, particularly with eligibility traces, had a significant impact in the real world?
It's had a monumental, groundbreaking impact. The most famous example is TD Gammon, developed by Jerry Tesoro in the early 1990s.
TD Gammon, backgammon, right.
This AI learned to play backgammon at a superhuman grandmaster level. It famously used a gradient descent form of TD with a neural network and eligibility traces.
Wow. Neural nets and TD lambda.
What's incredible is that it learned to play at such a high level by simply playing millions of games against itself, starting from purely random moves and without any explicit expert human knowledge of backgammon strategy.
Learned entirely from self-play. Amazing.
It used the concept of afterstates we discussed to efficiently evaluate the board positions after a move. TD Gammon stands as a landmark demonstration of the immense power of these algorithms for tackling complex tasks with vast state spaces, showing that AI could learn to master games through self-play and fundamental learning principles.
What an incredible deep dive we've had into these core algorithms. We've journeyed from dynamic programming's precise model-based planning through Monte Carlo's robust, model-free trial and error, and then into the elegant fusion that is temporal difference learning, culminating in the sophisticated power of T8 with its eligibility traces.
It's quite a progression.
It's clear that each method has its own distinct strengths and weaknesses, making them suitable for different kinds of problems.
Absolutely. To recap their fundamental relationships, we can think of them along a few key dimensions that truly highlight their differences and where they fit into the broader landscape of AI learning.
Let's start by summarizing dynamic programming. Hit us with the key points again.
Dynamic programming is inherently model-based, meaning it absolutely requires a complete and accurate mathematical model of the environment's dynamics, all the transition probabilities and rewards.
Needs the model. Check.
It bootstraps, updating its estimates of state values based on other estimates of successor states.
Bootstraps. Check.
And it performs full backups, meaning it considers all possible next states and actions from a given state when making an update.
Full backups, got it.
DP is incredibly powerful and efficient if you possess that perfect model, allowing for optimal policies to be computed directly.
Mhm.
However, it notoriously suffers from the curse of dimensionality, making it computationally intractable for problems with vast state spaces. Its strength lies in optimal planning, given perfect information.
Then we moved to Monte Carlo, which took a completely different path. What's the MC summary?
Indeed, Monte Carlo methods are at the opposite end of the spectrum in some ways. They are fundamentally model-free, learning directly from raw, unadulterated experience without any prior knowledge of the environment's internal mechanics.
Model free. Check.
They typically do not bootstrap within an episode, choosing instead to wait until the entire episode has concluded to use the full, actual observed return.
No bootstrapping. Check.
They perform sample backups, meaning they base their updates on a single observed sequence of events, a trajectory.
Sample backups. Check.
MC methods are excellent when a model is difficult or impossible to obtain, or when you can easily simulate numerous experiences. They can also focus learning on specific regions of the state space. However, their updates can be slow if episodes are very long or rare, and their reliance on full returns can lead to high variance in their estimates.
And TD learning sits right in the middle, blending these ideas in a really clever way. How does that summary look?
Precisely. Temporal difference, TD learning, is also model-free, learning from experience like Monte Carlo.
Model free. Check.
But critically, like DP, it bootstraps, updating estimates based on other learned estimates, but without waiting for a final outcome.
Bootstraps. Check.
It also uses sample backups, looking ahead to just one sample successor state.
Sample backups. Check.
TD learning truly combines the advantages of both. It learns from experience without needing a model, but updates incrementally after every step, generally making it more efficient and faster to converge than pure Monte Carlo methods, especially in tasks where immediate feedback is available.
And then TD takes that blend even further, making it a powerful continuum. The final piece.
Yes, TD truly unifies TD and MC by using eligibility traces to cleverly blend end-step returns across a continuous spectrum. It offers a sophisticated continuum of methods between pure one-step TD and full Monte Carlo when lambda.
A lambda dial.
Eligibility traces provide an elegant, causal, and computationally efficient mechanism to distribute credit for a TD error backward in time, linking current surprises to past actions and states, which significantly speeds up learning in many complex scenarios.
So with all these powerful methods at our disposal, how do we decide which one to use in practice? What are the key trade-offs and practical considerations for someone looking to apply these to a real-world problem?
This brings us to several crucial practical considerations. First, the fundamental model versus model-free trade-off. Do you have a perfect tractable model of your environment?
Big question first.
If so, dynamic programming is an incredibly powerful tool, allowing you to compute optimal solutions with great precision. However, if your environment is unknown or too complex to model accurately, which is often the case in robotics, financial markets, or game AI, then model-free methods like Monte Carlo and temporal difference learning become absolutely indispensable.
Okay, model availability is key. What's next?
Second, consider computation versus sample efficiency. DP can be computationally expensive per step due to its full backups, meticulously checking all possibilities. However, it can be data efficient if the model is perfect, as it doesn't need to experience the world.
DP is heavy compute, low data needs.
Monte Carlo and TD, by contrast, are computationally lighter per step, as they only use sample backups, but they often require many samples or experiences to converge to reliable estimates. You might need to run a simulation millions of times.
MCTD are lighter compute, but need lots of data. Makes sense.
Third, think about online versus offline learning. TD methods, particularly TD0 and SARSA, excel at true online incremental learning. They can make updates after every single interaction, making them highly suitable for real-time systems where decisions and updates are needed continuously without waiting for an episode to end.
TD is great for real-time learning.
Exactly.
I remember you mentioned function approximation earlier as the ultimate solution to the curse of dimensionality. How does that fit in with these algorithms?
That's critical. For problems with truly vast state spaces, far too many to ever store in a simple table, we can't use these tabular methods directly. This is where function approximation comes in.
Right, can't use tables for huge problems.
Instead of a lookup table, we use a more compact, parameterized function representation, like neural networks, linear functions with features, or tile coding. This allows the agent to generalize from learned experiences to unvisited states.
Generalization. That's powerful.
If a robot learns a good behavior in one room, it can apply that knowledge in a similar but previously unseen room. The beauty is that TD methods extend very naturally to function approximation, as demonstrated powerfully in the mountain car task.
Mountain card, okay.
Here, the parameter significantly impacts performance, showing how these eligibility traces help learning systems with function approximation make much better use of sparse rewards over time by effectively propagating that credit backward to relevant features or states.
So TD Lambda works well with neural nets and similar things.
Very well.
These aren't just theoretical concepts, then. They're truly driving real-world adaptive intelligence and solving problems that were once considered impossible.
Absolutely. These methods are the bedrock of systems that have achieved remarkable feats. We've talked about TD Gammon playing backgammon at a grandmaster level, purely through self-play.
Incredible story.
But they've also been applied to classic challenges like Arthur Samuel's checkers player, controlling complex robotic systems like the Acrobot, which has to swing up a pole, and even optimizing massive real-world infrastructure, such as elevator dispatching in busy skyscrapers.
Wow, elevators too.
In these applications, they can find solutions to problems with astronomically large state spaces that classical dynamic programming could never hope to handle. These systems learn to maximize long-term rewards by figuring things out for themselves, often starting with no prior knowledge, truly demonstrating the power of adaptive intelligence.
What an incredible deep dive into the core algorithms of learning. We've navigated the intricate world of adaptive intelligence, from dynamic programming's precise planning with a perfect model, through Monte Carlo's robust trial and error approach from direct experience, to the sophisticated blend of temporal difference learning and the elegance of TD with its eligibility traces.
It's been quite the journey.
These aren't just academic concepts. They are the bedrock of systems that can learn to play games at superhuman levels, control complex robots, and manage massive infrastructure, all by figuring out what to do to maximize long-term rewards, often without being explicitly programmed. They represent a fundamental shift in how we approach complex problem-solving in AI, moving from explicit programming to autonomous learning, truly enabling machines to learn, adapt, and make intelligent decisions.
They are powerful, adaptable, and a testament to the idea that by giving systems the right learning framework, they can often surpass human-engineered solutions.
So as you reflect on this journey, consider, in your own life, when do you operate more like a Monte Carlo learner, needing to see the full outcome of a situation before you truly understand its value?
Good question.
Perhaps when you try a completely new hobby or take a brand new route for the very first time, needing to experience the whole thing to judge it? And when are you more like a TD learner, constantly adjusting your predictions and actions based on immediate feedback and anticipating what's just around the corner?
Yeah.
Think about how quickly you learn from a quick glance at traffic conditions or a subtle change in a friend's expression, making continuous small adjustments to your plan. How might understanding these different learning paradigms, these ways of making sense of the world, change how you approach complex problems, make decisions, or even observe the fascinating learning happening all around you? The journey of discovery for us and for machines truly continues.